tonight's In-Reach event. There's coffee brewing and there's donuts and Girl Scout cookies for afterwards, so plan to stay and talk for a little while afterward. And speaking of social time, registration is open for our spring banquet, which is scheduled for March 7th. So if you would like to come to the banquet, go to the member portal, log in, and get registered for that. Let's see, we have an extra open house this month on the 29th. Somebody wrote to me and said, why only once in every 92 years? It's because a Saturday, February 29th, only happens once every 92 years. So I didn't look into whether the lunar phase was good or not. I figured that was a little bit going into the weeds. Anyway, so I'm going to turn it over to our In-Reach volunteer, Bill, and thank you for doing this. We appreciate you organizing these.
Well, my pleasure.
For sure.
My pleasure. So anyway, this is going to be a nice, if you've had a chance to kind of peruse the agenda, it looks good. And then we'll have a secondary handout that I will get that out as well.
Okay.
But anyway, without further ado, let's give it up for Tony G.
Yeah. What an entrance. Wow, that's really nice. So, my name is Tony Gojanovic, Tony G, that's what they call me. I guess we can turn off the light too.
Yeah, I think that,
Yeah.
we kind of figured that was a little better.
And
Is
I'm
that
gonna,
okay?
I think, is that okay for everybody?
Yeah.
So far.
Kind of
Except you won't be able to read your handouts, but that's okay. At least on one side. So hopefully you'll find this interesting. Hopefully I won't bore anyone to death. I won't be responsible for that. And I'm going to kind of talk about a little bit. This is not going to be like going through computer code, or we're not going to go through equations or anything like that. So I'm not going to mess anybody up with that perspective. Let me get this for the review here. Hold on a second.
Just getting started, so.
Excellent.
Just off the display.
Hey,
There we go.
Here's
All right.
a handout for you.
So let's go ahead and get started here. I'm going to do a little background. Not working? Yeah, there we go. So I've actually been a member of the DAS off and on for about 45 years, believe it or not. I started when I was 2 years old. That's so much, right? And a year and a half ago, I got an email from my employer at the time, and everybody in our company did. And they said, well, things aren't going for us well financially, and if you want to leave, now's the time to go. So I said, okay, well, I'll go ahead and go. And now I had all this time on my hands. So I thought, it'd be nice to get back reacquainted with astronomy again, because now I actually have time. When you're working, and all that kind of stuff, you don't have as much time to do this. So I went ahead and thought I'd get back into it. And I had two goals in mind when I did this. One was to learn enough astronomy to understand the articles in Sky and Telescope. Because I was getting those for years, and it's like you read, it's like dark matter, dark energy, interstellar dust. What are these concepts? And I also wanted to understand how modern astronomers know things. So like you're watching a show on TV, and they say, well, this planet is 1/3 or 1.3 times the mass of the Earth, or something like that. Well, how do you know that, right? What kind of information? So I actually wanted to understand how they know things, and maybe actually try my hand at getting the same type of data they got. And everybody's a different learner. And the question is how to best learn. Okay, so I'm sure everybody in here has tried different methods. You can watch TV shows. There's a million of them, right? How the universe works and all that kind of stuff. A lot of those to me are very irritating, because they just go off in so many directions. You can learn off YouTube. That's also incredibly irritating, because their AI programs send you in these weird directions, Like if you look at stars, you'll end up with you know, Kim Kardashian recommendations or something like that. You can learn, you know, read books or whatever. My learning style is I have to focus to an end project. So for me, I like to take a class and then have a project or something to work towards. Okay. Now, you can take a university course, but that's a pretty big commitment for time and money. Or they have these things nowadays which are really pretty neat. It's called MOOCs, M-O-O-C-S. Okay. And I got a list. A MOOC stands for Massive Open Online Course. So there's a bunch of companies nowadays that have these online courses. For example, you can have, you know, 100,000 people taking a course with you, okay, with these MOOCs. And I listed some. We're going to go through and talk about them on your sheet there. But the first one I decided to take was this called Exploring Space and Time from the University of Arizona. This is an online course. It's 11 weeks long, okay? You have a week of lectures, and then at the end of it, you have a quiz, okay? So you have to actually learn the material in order to pass the quiz. At the end of it, you can get a certification, okay, in astronomy. You don't get credits for it, like university credits. You'll get a certification, okay? So what I've done is I've listed on this sheet here a bunch of these MOOCs that I decided to go ahead and try on my road to astronomical discovery. And then it was like, well, that was interesting. Exploring space and time, they cover everything from the history of astronomy, you know, Kepler and Copernicus up to the Big Bang, cosmology, exoplanets. It was actually overwhelming. But this was actually pretty darn good, 11 weeks. But I wanted more, and you should always be careful for what you ask for. And I wanted to learn more about how astronomers really do astronomy. So there was another course called Data-Driven Astronomy. It was with Python. Has anybody heard of Python?
Yes.
Okay, quite a few people. Python is a computer programming language. It's very popular nowadays. It's been around for 30 years. Things like Google browser are written in Python. Instagram, if anybody uses Instagram. We have a small child here. Is written in Instagram. A lot of stuff on your phone or in Python is written in Python. But this was I think a 6-week course. And it was 6 weeks. It actually took me 6 months to complete. Okay, because it was not trivial at all. So this course, you're given real live astronomical data, and you're supposed to write a computer program to solve for it. So like what, for example? Well, let's say, for example, that you have a catalog of, let's say, radio measurements in the radio wavelength. Let's say you have 300 galaxies. And your assignment is to match up the visual counterpart in a master catalog that has maybe 10 million galaxies. Okay? So write a program to do that. How are you going to do that? Okay, now you say, well, I'll just match the right ascension and declination to 2 catalogs. But guess what? Right ascension and declination aren't precise measurements either. There's a certain degree of uncertainty around those as well. So now they're like, you have to develop the uncertainty measures for your catalog versus the master catalog and match them up that way. By hand. There's no point and click, right? So you do that and you'll find out it'll take about 3 weeks of runtime to actually do this. Wow, 3 weeks. That's not going to bode well on my computer here. So then you have to find an optimization algorithm to figure out how to parse the data set in the right way and then implement that, and it'll actually come down to about 2 seconds to actually do it. Okay. So can you understand why it took 6 months to complete this class? I did get a certificate in Python, by the way, so now I know Python as a language. So never enough. Last class I took was Analyzing the Universe from Rutgers. This is a different type of class. They actually gave you software. It was called DS9. Trivia question, by the way, sorry. Do you know why they call it Python?
Because it's
No.
a nest of snakes.
Restrictive.
Monty Python.
That's correct. So the
It's
developer of this, 30 years ago, he liked Monty Python's Flying Circus, and he called it Python.
So when you boot it up, it says now for something completely different?
It might, I'm sure it's in the user notes that says that somewhere.
Here's the velocity.
So this one, Analyzing the Universe, and we're going to go through some of these examples, was they give you a package, a data, it's a graphics visualization package. It was developed by NASA, but then Smithsonian Astrophysical Observatory took it over. And it's called DS9. And you can actually do image processing with it. It's a professional package. By the way, Python and this DS9 are completely free. So you can download them free of charge. Hackers like Python too, by the way, because you can really access internet systems incredibly easy with it. Anyway, DS9 was this one here. But that was I believe, a 6-week course on there. I have it listed. And that's been taking me about 5 months to complete. Because even though they give you a package, they still ask you questions in the quiz, which are not trivial. Okay, so it's been quite challenging here, and but anyway, we'll talk about that a little bit more. I also have listed on here some of these free downloads. So DS9 imaging, the Python, if you're interested in learning this language. There's a book on Amazon as well. It's called Python for Everyone. And if you are into programming, this would be an excellent book. This costs $10 on Amazon. There's also a free PDF version, which is authorized by the author online as well. Okay. So I went through this book and did every single exercise in there. So that's how I learned Python. It's actually pretty easy. And then also you need an editor, which is called Atom, and we can talk more about that later. So anyway, what I ended up with, I did understand how to read sky and telescope finally, okay, using this class. And I did understand how modern astronomers know things. And I'll show you how that works too. How much do these courses cost? So the company I use is a company called Quasar. And they really cater more to the business world for like certificates and stuff, but they have a lot of these cool courses behind. And the way it worked before was you'd have to pay for each course, so maybe this one would be like maybe $140 or something like that. But now they have this pricing where it's $50 a month subscription and you can take all you want. So theoretically you could take 3 courses if you're incredibly motivated in a month or 2 months and then cancel your subscription, okay? If you have nothing to do 24 hours a day, 7 days a week. But, you know, it's like you think $50, and it's like, well, how much do I spend on my TV, you know, every month, or how much does an eyepiece cost, you know? We can't talk about those things because my spouse is here today. So we're not going to talk about prices on anything. Anyway, and then I learned a few other things today, and this is something informational for everybody. Today, modern astronomy is a world of software telescopes. And what that means is that, you know, when I learned astronomy many years ago, or whatever, I had this image of astronomers with the pipe and the coat and tie, sitting inside of an instrument all night taking a picture. Nobody does that anymore. They sit in control rooms that are well lit, and they actually do the imaging that way. You can actually do astronomy on a beach in Miami with a laptop today, while your telescope is on the other side of the planet, okay, taking pictures. So the whole thing is a lot different than it once was. The other thing too is that it's data intensive, so you can generate a petabyte of data in one evening, which is 1 million gigabytes. That's one instrument, one night, somewhere. So 1 million gigabytes is 4,000 of those laptops a night filled up to the brim with astronomical data. I was watching a show on TV about it. You can't even transfer this data over the internet, okay? So they download them into like these little, I don't know, like hard drive units or whatever, and then they mail them off to whatever university wants them. And then they download them maybe to a supercomputer, okay, or a large database. So it's not like, again, be careful for asking for more data.
Yeah.
And large and complex data sets are simply no longer easy to solve. So it makes them very, very difficult to solve today, okay? And it's not just astronomers working here. You've got database administrators, programmers, software engineers, a lot of other people involved in this whole process.
Tony?
Yes.
Question, is that because with such large and complex data sets, it's difficult to see patterns?
It's difficult to even download the software in anything usable. So if I'm a user, for example, how would I download any information onto my laptop, right?
Yeah.
So you would have to go to the supercomputer center and actually ask for time and all the rest of it.
Okay.
So what they're doing nowadays is sampling the data instead. And you can still see patterns, but we're going to talk about machine learning algorithms too, where machines are actually used to try to learn the data too. But they're not as effective as you think they might be. Okay? They're not as wonderful as everybody thinks they are. And really today, it's about thinking in a computational way when designing, conducting, and analyzing observations and simulations. So this is where the computational astronomy comes into play. So, next is, so today the opportunities for an amateur to participate unparalleled to prior times, but too much data for professionals means more opportunities for citizen scientists, right? So if I'm a researcher at some university and I've got all this data, I have no staff, I can't look at it myself, but maybe I have all you to help me, right? And we're going to talk about how that works, okay, where they have citizen scientists actually looking at this data. And, even 30 years ago, if you wanted any data, it would be impossible to get any astronomical data. You'd have to go to a university, talk to a professor, get some data. Today you can pull it right off the internet, right? It's available to everybody. Not all of it's good though, so you gotta be careful.
Yeah.
Computational astronomy basically means taking a list of numbers like this. These are called flux magnitudes. Doing some kind of computation and then making a picture. Okay, so that's what computational astronomy means. Okay. So you're basically doing discovery through software. And I'll show you some pretty cool examples of this. Now, the question is, can an amateur participate in computational astronomy? And the answer is yes. So there's two ways you can do it. You can do it yourself by programming it, building it from scratch, okay, which is not easy. Or you can take web tools, plug and play, which is a lot easier learning curve, okay? Got a question? Okay. So we're going to talk about where you can get both kinds of programs or software here. All right, see what's next. Why is amateur computational astronomy kind of fun or interesting? A couple of reasons. It's an alternative complement to visual astronomy. It can be done on cloudy nights, no telescope required. I was playing with some of this stuff last week when it was all cloudy. Sometimes it's too cold, I don't like to go outside. And not all of us are good visual astronomers either. I have a friend, he's an astrophotographer, and we went like 70 miles east of Denver and found some random farmland and set up our telescopes. And it was beautiful out there, it's really dark and all that. And then 11 o'clock comes around, it's like, well, I'm done, I'm ready to go home. He goes, well, I'm just getting started here. So I'm like, well, okay, maybe that's not for me, so maybe the computer thing is a little bit more for me. But it can be done as a complement too. You have access to the best astronomical instruments in the world. So a lot of times people ask me like, what kind of, telescope do I have? And I'll tell them that I have actually a 2.5 meter reflector. They're like, really? A 2.5 meter reflector? And I said, yeah, it's called the Hubble, and it's circling us right now. I believe I paid for it, right? And you can download the images from it. Okay, the Chandra X-ray Observatory, that's mine too. You can download information. Okay? And
Can we borrow it sometime?
you can. Actually, did you know an amateur can use the Hubble? Because it is a publicly funded project. Okay, you can actually apply for time. Now, of course, they're not going to say, well, let me look at the moon or something. They're going to, want some kind of real project. But you can actually use the Hubble as amateur. You can look at multiple wavelengths of information. So if you're a visual astronomer, typically we look at that. Connect with the professional astronomy world. Again, what they're looking at, professional astronomers you're looking at as well. Be a detective and find interesting patterns. There are cases of amateurs finding things like supernova or other interesting features by looking at astronomical data. Project-based learning for focus, experiences for focused learning. Part of the problem with astronomy, it's too vast. So you can actually pick one project and actually explore it in more detail, which is really the way to go that I found. And it's preparation for other courses and learning experiences. So if you're a young person and you want to go into astronomy or even any kind of sciences, you're going to have to learn computation, most likely. You're going to have to learn how to program today. So by learning this, maybe in high school or develop, maybe doing a like a science fair project that'll help you later on. And the best part, which everybody will like, it's absolutely free. Okay, so the vast majority of these tools are free for now. I did see that some observatories in the future, the big ones are the gigantic telescopes, may start charging for data later on because they're so expensive. But I just building something the size of a football field is going to be not cheap. You can analyze supernova remnants. You can cross-match to explore data in many wavelengths. You can find exoplanet data. There's an exoplanet data website. You can do classification of galaxies. You can decipher X-ray sources. Find gravity waves. Okay, that is available online for free. Crowdsourcing. We're going to talk a lot about citizen science projects and much more. Is this interesting so far?
Yes.
Okay, nobody saw him fall asleep? No one died of boredom yet? Okay. If you died of boredom, how would you know? How would I tell you? The guy who's not moving, I guess. All right, so here's a DIY project, for example. If you do astrophotography, you probably do image stacking. So this was a project that I worked on in one of the classes. These are some pictures. These are done in the radio frequency range. And they don't look like pictures of anything in the sky, but each one of these little pixels represents energy fluctuations, okay, like in the radio region. So the assignment was to stack these images, okay, which you do through a program. This is the DIY approach, and end up with a picture like this. And the question is, where is the pulsar signal in this? The pulsar signal, when you add those up, is right here in the center. Okay, so that's an example of a do-it-yourself project using a computer programming language. So it's pretty trivial if you got 3 images, but if you have 1 million images, it's no longer an easy task, right? So this is kind of and there is no point and click. You actually have to kind of run the software yourself. But that's kind of tough, and I'm not really a big fan of do-it-yourself. But I do like web tools, and this is a plug-and-play tool. This is DS9, the software from the Smithsonian, which I was referring to. This is freeware. And it's really kind of designed for X-ray data. This is the from the Chandra X-ray satellite in orbit. This object is called 3C273 in the Virgo constellation. It's an active galactic nebula, nucleus. This is what the Hubble image looks like. But this one is done in the X-ray region. Okay, so you see how it's different? See how much more detail you have? And you see these big things right here? Those are jets coming from this nucleus. So what's in the center of this? It's a gigantic black hole, okay? Now the reason it's black here, this is a close-up region, and this is all stuff you can do for free. You just pull it up. There's a catalog of things you can pull up. It's not because there's a black hole, it's black because the Chandra sensors are saturated because the energy is so bright. It's like overexposure. And there's even a little jet here. So one of the questions was, well, how long are these things? Well, you can count the pixels because each pixel is about a half arc second or something like that. And it turns out that these jets are 35,000 parsecs long. So a parsec is 3.2 light years roughly. So it's 35,000 times 3.2 light years. That's pretty big.
About 100,000.
Yeah, 100,000 light years. Bigger than our galaxy, right? If you look at both sides. And there's even a little jet coming out here. So one of the cool things about this is you're actually exploring something. This is real data. This is a subject of real research. So it's not like something phony or whatever that you can actually examine yourself. So another question is, well, how far away is this object? Well, they give you, is everyone familiar with redshift data? Doppler? So Doppler shift is, if you're like in if you hear an ambulance and it's coming at you, it sounds different than when it's going away from you. And the reason is because the sound waves are compressed versus stretched out. So the same thing happens with astronomical objects. It actually gave us a redshift data, and they asked that class that I took, to actually calculate the distance. And you can do it yourself. And it turns out to be 2.4 billion light years away. Just by using this piece of paper and some basic formulas they gave you. It's amazing. I'm an amateur, and I could figure this out myself, right? I mean, doesn't that just, to me, it's just amazing, right? That you can actually do this yourself. And, I mean, 100 years ago, this wouldn't even exist. It's got a magnitude, by the way, of 12.9. So 2.4 billion light years away with a magnitude of 12.9. So another thing is, well, how bright is it? So what you can do with this free software is you can draw a circle here, and you can actually pull up some analysis tools to do a light curve, a spectral fit. And you can actually determine the ergs, which is a way of determining the light intensity for this object. So for a square centimeter, it's about 8 to the minus 12 or something like that. You can round up to minus 11 or something. So how do you calculate how intense this object is? So imagine the Chandra's got a 1 centimeter thing, it's getting this much. But the object is radiating out in every direction, right? So you have to calculate a sphere around this object that has a radius of 2.4 billion years, 2.3 billion light years, and figure out the surface area in square centimeters. Is it possible to do? Yeah, but it's algebra too. So you've got this Chandra, you got this object, it's picking up this density here, okay? And now you have to find out what it is for every single point on that surface. So you figure out the area of a sphere, the radius. I figured it was actually 2.3 billion. That's how many centimeters, 10 to the 27 centimeters. When you figure it out, you multiply that by this, you get 10 to the 44th ergs. So that's 175 billion times the energy of our sun. But that's not right. That's my estimate I looked it up online, the true estimate is 4 trillion times our sun. So imagine our sun tomorrow, if it's out, and imagine it 4 trillion times brighter. That's how bright this thing is. Okay.
Imagine the Earth going up in a puff of smoke.
That would be. So, let me put it another way. So, our the absolute magnitude of our sun is about 4.8 if you standardize to 10 parsecs, okay? So on that scale, this is a minus 26.7. So at Pollux, I think is 10 parsecs away, 32 light years. This thing would be as bright as the sun.
Wow.
So you can see how bright that is, right? Anyway, luckily we don't live too close to them. So that's kind of the fun things about these kind of free software things that you can do. Here's another one I put out there. This is the Cas A supernova remnant. This one happened in 1650 AD. Nobody saw it. It's not really recorded in any records for whatever reason. This is what it looks like in the visual spectrum. So you can actually pull this up. This software will pull up any kind of visual equivalent. But this is what it looks like in the X-ray region. Okay.
So those two images the same scale?
Yes, they are.
Okay.
They've been scaled the same. So you can see there's a lot more variety with the X-ray region than the visual one. And you can do stuff with this one too, with the same free software. Like, you can actually look at different regions. You can make a circle, and then you can do a quick energy spectrum. So these high peaks right here are silicon, and then you've also got iron here. But you can see how weak this one is here. So what this one's saying is this is an asymmetrical explosion of some kind. Okay. And this little bright thing in the center right there, that's a neutron star, or pulsar today. Okay. But you won't see this in the visual wavelength, right? Because it's in the X-ray region. So this is where it's kind of fun to play around with different things. Now, let's say you're not really interested in this too much, but if you're a visual astronomer, let's go ahead and pass these out.
You want to do half and half?
Yeah. What I did for you, for these two objects that I looked at here, they're actually fun to try to find. So if you look at the 3Cs and 273, that's the Quasar. I have a finder chart here. So up at the top it says 3C273. It's about 12.9 magnitude if you want to try to find it. It is in the Norton Sky Atlas too, as well. You can try to actually look it up if you're interested in hunting for something. The other side is this image right here, which is Cas A, and it's on the other side. And you can actually try to find this one too. So you can, if you want to play around with this, I actually want to try to find these myself. So where I said I wasn't a very good visual astronomer, I actually want to give this a shot and see if I can find it. Because it makes it more interesting now that I know what these things are like, right? Anyway, you can play around with that a little bit. On that one, the Quasar one, if you look at, there's Bob King from Sky and Telescope wrote a nice on 12 quasars for the spring evening, and you can look that up and see what other objects he has. So this is kind of fun, just to play around with it a little bit. And then let's look at this picture. This is what that Cas A looks like from NASA. You will not get this if you try to image it, because this is actually the Spitzer infrared.
Wow.
It's the Hubble visual, or visible wavelength, and it's also the Chandra X-ray image as well. So this is actually 3 different wavelengths of light that have been combined together. if you try to do a visual, I've seen some online of some amateurs, you just kind of get a little wisp, you know, but the rest is pretty neat. Anyway, never amazes me the things that are out there. Truly doesn't. So what do you need for computational astronomy if you're going to do this? You need an internet connection or a laptop. How much does that cost? Well, it kind of varies. You can also use the computers at the library as well. Oops. There we go. I also have a list on your sheet as well. You need reliable data. So if you do yourself or web tools. And I put reliable because there's a lot of junk out there. You know, we've heard of fake news. There's fake data, there's fake science out there too. I was looking at one catalog this amateur put together, and nothing against this amateur, but he put together all these different catalogs of objects, and then I plotted them out, and he had a blog, and there's a professor who came on and said this isn't right. So you got to be a little bit careful where you're getting your information from.
Do you have any tips for that?
Yes, stick with reputable sources like Harvard or a university or something like that. Somebody that has a vested interest. If you want to do it yourself, there's a lot of development software out there. You can use Python. A lot of this, it's all free. All this stuff here will be a steep learning curve though. Online courses, these MOOCs, okay, that we have listed there. Massive open online courses. They are free if you want to view them, but if you want to like do the quizzes and the homeworks and stuff, there's usually a cost associated with it. Okay. I personally like to do the assignments. A lesson plan or a guide helps. So if you want to try to do this at home, if you pull up a gigantic database, you don't have any idea what it's going to be. So it's good to have a guide. And I'll talk about where you can get some guides. A lot of universities have classes where they have the guides online. And you can download them, like how to do it. Citizen science tools, we're going to talk a little bit more about this. Like Galaxy Zoo, exoplanets.org, nasa.gov's got a ton of stuff for projects. It's all free. And then the last one, may or may not be doable, it's patience.
Yeah.
Right? So when I was working on this stuff, I have a nice finished presentation here. But when I was doing a lot of that computational work, it was like, just smash this computer over the head, right? I mean, error, thousands of them, but eventually that's how you actually learn about the material as well.
Don't you need a rather large brain and vision to manage
Yes.
all this?
Oh, I don't know, maybe.
Well, it's pretty hard, I mean, R is severe.
You know, a year ago, I didn't know one command line in Python at all, you know. I couldn't even write my name to the screen. And then it's like, how do you approach anything? I guess in this case, one line at a time, right?
Yes.
One line of code at a time, right? Now, the next one this is a fun one. So that's kind of the, you know, that's a little bit more intense. If you really want to take your hobby to the next level, that's the way to do it. This next one is, has anyone heard of Zooniverse? No, not many people. You have.
Yeah.
Zooniverse is like the best thing ever. And it was actually, these are called crowdsourcing, and the guy who developed it, I actually have his book here, just came out in January. It's called The Crowd and the Cosmos by Chris Lintott. And he's a astronomer, an astrophysicist, and he had the problem, like most astronomers do, too much data. So he couldn't deal with all this information he was collecting, so he built this website called Zooniverse to actually parse out the data to the public. So instead of just him looking at stuff, It's hundreds of thousands of people looking at this data and classifying it. Okay? And it's the human classification of objects, because humans are best at classifying things. Machines can't still do it as well as a human can. So they have Galaxy Zoo, okay, which is actually, I'll show you an example, classifying galaxies, galaxy types. Moon Zoo, if you want to classify craters on the moon. Solar Storm Watch, this is actually looking for solar storms that could be approaching the Earth. Space Warp, this is looking for gravitational lensing. Star Notes, this is a really cool one. The Harvard Observatory, at the beginning of the last century, they started taking photographs on glass plates. They have 500,000 glass plate negatives. And they have a logbook associated with all these glass plates, but guess what? Yeah, they scan them all in, but they can't determine which plates belong to which logbook. So they're actually asking the public, and I'll show you, this is actually a really cool one. Hubble Asteroid Hunter, again taking pictures and looking for asteroids. And this is just the astronomy stuff, but they have stuff for like zoology, looking at penguin populations in Antarctica, all sorts of things too. And the whole idea here is you've got a bunch of people, and eventually their opinions should converge on the right answer. And it also forms a training set for machine learning. So eventually they want machines to do this, but if you let a machine just run on by itself on the data set, it won't come up with anything. You have to actually train it. So they use these for training sets. Okay. And I'll show you how this works too. So here's the Galaxy Zoo one. So the way it works is they give you these observations of galaxies. They have the citizen scientist look at them. They give you a set of instructions. Is it spiral, elliptical, or merger? So you got all these people looking at the same image, and they eventually will come to a consensus on what type it is. And then, from that, the scientists will actually determine properties of this, put it into a digitized form, and then feed it into this machine to learn. And then in the future, the machine will be able to go ahead and start analyzing the data itself. One of the assignments in that class, the data-driven astronomy, was to actually build a machine learning program. Anybody want to see it run? Sure?
That's why we're here.
Are you sure you're here? Just not for my...
Your effervescence.
There's donuts too.
There's donuts too.
Oh, yeah, donuts.
So anyway, we'll look at... So basically... There's power cord. Let's see here. So one of the things was what you do is the assignment was take a training set from the Galaxy Zoo, and this is awfully tiny. So you can run this in Python. And see if it works. Oh, yeah. So what you do is you actually take a fraction of the training set. So we're going to take, let's say, half of the Galaxy Zoo data, train, and then we're going to use the other half to see how well it works. So we use half. So this is what it looks like. So what it did is it took, this is called a confusion matrix, right? But this is the predicted class, and this is what the actual class is according to Galaxy Zoo. So the program I wrote said that 34 galaxies classified as mergers were actually ellipticals. See what I mean? Here it said my predicted class is spirals. I have one, but it was actually an elliptical. Here it says my ellipticals were actually spirals. So anything off this diagonal is wrong, right? According to the Galaxy Zoo. So you can see the ones that got right are in the center there. It's about 80% of that. That is correct too. Anyway, that's how Galaxy Zoo works. And that's what it's used for, I should say, not what it's used for. All right, so let's go back to our presentation here. So let's go to Zooniverse and take a look at it. This is really fun. This is if you want to just play around with something and you're kind of bored, it's cloudy outside, whatever. Oops. And actually, let me think here. I think I pulled it up already. We'll talk about that one. Let's just go here. Oh, here it is. Galaxy Zoo. So here's how it works. So what you're given is a set of images, okay? And this is free, open to the public, just log in. And it's going to ask you a set of questions. Is this a smooth and rounded with no sign of a disk? So here's your instructions. Is it smooth? Does it have any features? Or is it a star artifact? So what do y'all think that one is? Smooth, probably? Okay. Now imagine this, though. We're going to have 100,000 people doing this, or 1 million people. So some people are going to get this wrong. But probably everybody here agrees that this is smooth, right? So you see how a consensus kind of formed here? Probably no one's going to say it's a star artifact. So then you click on it, and it goes into the database. And then you do the next one, and it'll ask you, is it completely round? Is it in between, or is it cigar shaped?
In between.
So you click on that, and go to the next one. And is it merging? Does it look like a major disturbance, minor disturbance, or none?
I'm gonna go for none.
Probably none.
Yeah.
And that's how you classify these. So you keep, and then it asks more questions. Is there a ring? Is there a lens or an arc? A regular? Blah, blah, blah. So it keeps leading you through these questions. And, you know, eventually, this will eventually form the data set for the machine program. Now, some people have been looking at these and they find other things in here too. And some people have actually made discoveries. Okay? Because just think, a professional astronomer doesn't have time to do this. So let me show you some other projects here. This is called Zooniverse. So, for example, there's projects like looking at, what's this one? Cardinals. There's looking at mapping historic skies, wildlife watching, looking at herring populations. So these are all other fields that are asking the people, the public, to help them.
What's the one labeled weird?
Notes from nature, how weird is that? Yeah. But here's the one I was talking about, the star notes. This is the one about the Harvard Observatory collection. And it gives you a whole thing about, you can learn about these women astronomers basically who did this. And what it worked, let's see. And you can look at the different astronomers' logbooks, like Anna Jumpcannon, Wilmina Fleming, Swan Levitt. But what you do is you choose some person here. And here's an example of a logbook. So what you're going to do now is you're going to find, you have to read the tutorial on how to find the numbers, but anything with a letter, number combination refers to a plate number. So what you have to do here is they ask you, are any plate numbers visible? And you say yes. And then you go next, and then what you do is you draw a little box around it. And then you actually type in the numbers. And okay, so now I have one number that I can actually add to that database.
And they trust you. That
Well,
you're putting in the right.
You could be completely wrong, but imagine 100,000 people doing this
Yeah.
eventually.
Yeah. So it's consensus as well.
One of the cool ones was called, there was one for the global climate change one, and they were looking at records from the last 1800s for temperature readings anywhere across the globe. They wanted a good, understanding. So who was around the globe in the 1800s and recorded temperatures every 4 hours? There was somebody. It was the British Navy, right? So they have hundreds and thousands of log entries from the British Navy in the 1800s of temperature readings taken every 4 hours virtually everywhere on the planet. So people are going through those now so you can get an idea of what climate change was, compared. But when people are reading this, they're reading other things in the logbooks too, like mutiny today, captain killed, or something like that, right?
Yeah.
So there's other things like, maybe, had a bologna sandwich or something here, but there's other things that are also associated with these types of projects, which are really kind of fascinating too. Anyway, that's Zooniverse. I'll tie it up here in a little bit. Does that sound interesting?
Yes.
All right. And then I got a few more web-based tools we'll look at, which are free. And I think you'll like these a lot too. We've talked about Zooniverse. It's listed on your paper. I'm not going to talk about NASA because that's an incredibly big website that could take days to go over. Las Cumbres Observatory. That's a private observatory. Has anybody heard of that? And that's actually, it was created by a ex-executive from Apple. He was one of the founders of the Mac. So I'm sure he retired with no money at all. But this is his project, and it's actually a global telescope network. But you can actually pull up stuff on, for everybody, for example. And there's a lot of stuff on education here. So if you want to find stuff like on how to do different projects and stuff, this is a very, I like this one a lot. I use this one a lot too. A lot of free stuff here too. And then the last one we're going to talk about is this University of Nebraska interactive site. This is the coolest thing ever. Nebraska puts cool stuff together. And this is a bunch of simulations they put together on anything, just about everything astronomical. So it's got stuff on how different things work. And I'll show you one of these the season simulator is one of my favorites. So if you're getting into astronomy and you want to understand how the seasons work, for example, you can pull up this simulation. Okay. So there's the Earth and the Sun. There's the month. This is the angle for an observer. So we can move the observer to our latitude. So move the little person there to about 40-ish roughly, right? And then you can see the angle of the sun today, or roughly, we're in February. And you can actually start this neat animation.
Nice.
So it actually shows you how the angle of the sun will change as the months tick along here, and then the kind of the thing here too. So here we come upon summer solstice right there. So you can see the sun will be pretty much directly overhead, right? It's going to be pretty bright. And then it kind of goes the other direction as the season starts to fade or whatever. So this University of Nebraska site has a ton of stuff like this. You can change the views too, like that. And you can kind of see where things are going. So if you want to play around with this tonight, this is a fun one. You don't have to do the animation. You can just move it around like that manually too. Let's see what another fun one is. Let's see. Moon phases. They even have a thing on telescopes. This is a kind of a neat one. So if you don't know much about how telescopes work, you've got a picture here. You can change your aperture. So for example, a 6-inch. And I can adjust my focus here. Oops. There we go. So that's roughly what a 6-inch refractor would look like with a 10mm eyepiece. Right? You can look at like Saturn. And it gives you other things too, like the resolution in arc seconds, okay? The magnification and the field of view. And you can play around with it a lot. So look at the resolution when I change apertures. See how the resolution changes? The magnification doesn't change a huge amount, but the resolution does. So this is a question, why do you need a bigger telescope? Well, because it's the resolution that's the most important, right? More than the magnification. But you can see that this is again a kind of a simulator for that. I'll show you one more here, because there's a ton of them. They even have a thing on let's see, sun and solar energy, binary, Milky Way galaxy, cosmology, solar system, rotating sky. Has anybody heard of the Hertzsprung-Russell Diagram? Okay, so that's the example. That's the stellar evolution chart. And you have the sun on the right there, our sun, and a star, which is right here. And you can see the luminosity is on the left, the temperature is below. So if I move this star over on temperature so it's hotter, but the luminosity becomes lower, okay, it gets very tiny. And then you get it up into the giant stages up here. So you can just see how things compare for luminosity against our sun or whatever. And then my favorite one, and I'm going to, not my favorite one, I have a ton of favorite ones, I shouldn't say that. They're all my favorites. It was this one, Renaissance Astronomy.
Oh, yes.
So, Ptolemy, the guy who thought of the Earth-centered universe, wasn't completely wrong. I mean, his model actually does work for a lot of things. But here is an example of, if we're in the center, let's say that's the sun and these are planets, but let's pretend like the blue is the Earth, and we're going to make that in the center. So this is now what the orbital motions would look like. So back in the day, before we realized that the Earth wasn't the center, they actually thought this was the picture of the way it looked. Actually, this model does predict things pretty well, but they do get into problems when you try to predict too much. You know what I mean?
What's the name of that? What's the URL for this website?
That one is on your sheet, and that one is the UNL, that astronomy simulation. So that's astro.unl.edu. Anyway, so if you want to learn astronomy, you want to try different things, you can do that. And then I'm going to finish with one last slide, and then we'll be done. So I was thinking about this a little bit. It's really hot in here. And what is, if big data is out there, what is the future of visual astronomy in the age of big data? So I don't expect anybody to answer this, but because I was thinking about this, should I buy a telescope at all? But the reason is you should buy a telescope because, you should at least look up every once in a while, because there still is pretty amazing to see whatever, Even the guy who did the Zooniverse, who created it, he says he still goes out with his telescope and still looks up at the sky, even though he's an astrophysicist, he doesn't really look at the sky. Does that make sense? So it's kind of like going to the Grand Canyon, right? It's still a pretty amazing sight even when you're we're standing at the edge. So visual astronomy, I think, is really most alive in clubs like this here. Professional astronomers don't look at the sky anymore, but we do. All right, that's all I got.